Hi everyone, this is Mrs. G.A. Today we're going to talk about radical expressions and rational exponents. But first I have a warm-up for you. So I want you to look at this list of numbers, circle the numbers that are perfect squares, and put a box around the numbers that are perfect cubes. So pause the video and give this a try, and we'll check your answers in just a few seconds. Okay, go ahead and check your answers here. So you can see that there are a couple numbers that are both perfect squares and perfect cubes, 1 being one of them and 64. So here we have 1 squared, 2 squared, 3 squared, 4 squared, 5, 6, 7, 8, 9, 10, 11, 12, 13 squared. And then for the cubes, 1 cubed, 2 cubed, 3, 4, 5, 6, 7, 8. So these are numbers that are just good to recognize. Maybe the higher ones you won't see them as often, but certainly some of the lower numbers, if you can just recognize these numbers as perfect squares and perfect cubes, it will make it a lot easier to help you simplify radicals. All right, so before we start talking about radicals and rational exponents, I want to do a quick review on how to simplify radicals. So here we're going to be simplifying square roots, a cube root, and even a fourth root. So remember, for a square root, we're really looking for a number squared to help us simplify. So there's a couple different ways you can approach these. One, you can look at 72 and then think of the perfect squares that you know, and then ask yourself, are any of my perfect squares divisible into 72? So 72 is divisible by 9, which is a perfect square, and it's 9 times 8. And then we think of 8 and we say, is that divisible by any perfect squares? Yeah, it's divisible by 4, which is a perfect square. So it's 4 times 2. So this will simplify. The square root of 9 is 3. So that's going to go to the outside of our radical. And the square root of 4 is 2. So that will also go to the outside of our radical. And then you can see what we have left behind is simply this 2. And then we can look at our variables. So again, we're looking for groups of 2. So I look at each exponent and I say, how many groups of 2 can we pull out of x to the 4th and x to the 6th? So again, on the outside it's 3 times 2, which is 6. So I say, how many groups of 2 are in 4? 2, so it becomes x squared. And then how many groups of 2 are in 6? And that's 3, so it becomes x cubed. And then inside our radical, which is called the radicand, we just have 2. Now this is one way that you can simplify. Maybe for you it's not as easy to think of the perfect squares that are divisible, so you can actually just do a full prime factorization. So just a different way of approaching this. We're going to factor it completely. So maybe we start the same way, like 9 times 8, or whatever you see is divisible, and then you keep factoring until they're all prime numbers. I like to circle my prime numbers so I know that I'm done. And then we can list those out inside the square root. So we have 2 times 2 times 2 times 3 times 3. And then for even the x's, we can list those out. X times x times x times x, y times y times y times y times y times y. So a little more time consuming, but that's okay. And then since it's a square root, we're looking for pairs of numbers. So you could circle or highlight the pairs. So there's one pair, a pair, 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 and pair. So for each pair of numbers, one of those numbers is going to, I like to say, move or escape out to the front. So we have a 2 times a 3 times x times x times y times y times y, and then what we have left is 2. And you'll notice that we get the same exact answer that we got above. 6x squared y cubed root 2. So a different way of doing it, definitely a little more time consuming, but still just as effective. Now let's look at part B. So here we have a cube root. So we can think, okay, what cube roots are divisible into 40, or 40 is divisible by what cube root? So we know that 40 is 8 times 5, and we know 8 is a cube root. So the cube root of 8 is 2. So that will simplify out front. So we have 2 cube root of 5 is still left inside, x cubed, and we have a cube root, so we say how many times does 3 go into this exponent of 3, and it's once. So it's just 2x times the cube root of 5. Or we can use that same method that we did before. So you could do the full factorization. So you factor it all the way down. So maybe this time you see 4 and 10, and then you see 2, 2, 2, and 5. So it becomes the cube root of 2 times 2 times 2 times 5 times x times x times x. But this time, since it's a cube root, we're actually looking for groups of 3. So we have a group of 3 here and a group of 3 here. So for each of those, 1 moves out front. So 2 moves out front, and x moves out front, and we get that same exact answer. So again, just a different way of approaching simplifying. So let's look at part C. So again, it's a square root, so I'm going to ask myself, 112 is divisible by what perfect square? So if you try dividing it by 4, let's say 4, it does go in, and 4 is a perfect square. So you get 28. And then you look at 28 and you say, oh, is that divisible by any perfect squares? And it is. Another 4. So then that leaves us with 7. So for simplifying that, square root of 4 is 2. So that goes to the outside. Square root of 4 is 2, so we put another 2 on the outside. And then let's look at our exponents here. How many times does 2 go into 5? It goes in twice, x squared, but there is going to be 1 left over inside. And then we ask ourselves, how many times does 2 go into 9? And it goes in 4 times, so it's going to be y to the 4th. But again, we will have an extra y left over. So what we have left over inside is that 7, and then an x, and then a y, like this. And then we just multiply the numbers on the outside. So 4 x squared y to the 4th times the square root of 7xy. All right, let's look at this last one. So here we have a 4th root. So maybe you don't know off the top of your head perfect 4th. So here we can actually just do a factor tree. So we'll factor it all the way, or as much as we can. So let's say, you can divide it by whatever you want. So 2 times 24 could be a starting place. 2 is a prime number. And then we can do 2 times 12, 2 times 6, another prime number, and then 2 times 3. So there's our prime factorization, so we can list them out. This is a 4th root, and our prime factors are 2 times 2 times 2 times 2 times 3. So this time we have a 4th root, so we're actually looking for groups of 4 to allow us to simplify. So here's a group of 4. So then that gives us 1, 2 out front. And then we just have that 3 left on the inside. So 2 times the 4th root of 3. So however you are most comfortable simplifying is what you should do. If you can find a way to be a little more efficient and to save you time in the long run, that's always a good thing. But just remember, you can always do the prime factors and then look for groups that match your index, that little number above your root sign. So now that we've done our quick review on how to simplify radicals, we're going to talk about how we can rewrite radicals in different forms. So it turns out that any radical expression, meaning any expression with a root, can be written with a rational exponent. So a rational exponent, rational is just kind of a fancy word for a fraction. So it can be rewritten with an exponent that is a fraction. So if I have, we'll start by going from fraction, exponent to radical. So if I have x to the power of a over b, the a, the numerator of our exponent, stays inside the radical, or it becomes the exponent of our base, and the denominator, the b value, becomes what is called the index. So this little number right here, we call that the index. And then we could also rewrite it like this. This is equivalent to this. So whether you want to put the exponent inside the radical or outside, either way is fine. Now we can also go backwards. So if we start with a radical expression, we can rewrite it to have this rational exponent. So notice what used to be the exponent of our radicand, which is the inside of our root, now is the numerator, and the index is the denominator. So when I do this, I like to remember the phrase inside out. So I say inside out, meaning again the numerator becomes the exponent of the inside, and the denominator becomes the index, which is on the outside. So it is really useful to be able to rewrite rational exponents as radicals or vice versa. Another quick reminder, if you have a negative exponent, it does not make your answer negative. What it does is it actually causes the term with the negative exponent to become the reciprocal. So if that term was originally in the numerator, it's going to flip to the denominator, or vice versa. So I just want to remind you guys that a negative exponent does not make your answer negative. All right, so now we're going to practice rewriting these expressions in radical form. So notice that all of these expressions have rational exponents, and then we're going to simplify when we can. So here we have 16 to the power of 3 over 4. So remember, inside out, the 4 becomes our index. So it's the fourth root of 16 cubed. So that's how we can rewrite it. Or we could also say the fourth root of 16 cubed. Either way is fine. So we can actually simplify this. The fourth root of 16 is actually 2, because 2 times 2 times 2 times 2 is 16. So this actually becomes 2 cubed, which is 8. So by rewriting this as a radical expression, it does make it easier for us to simplify. So again, the fourth root of 16 is 2, and then we cube it, getting 8. All right, let's look at this next one. Here we have negative 7 to the power of 2 over 3. So remember, inside out, so it's going to be the cube root of negative 27 squared. So here, the cube root of negative 27 is actually negative 3, and then we can square that to give us positive 9. And there you go. So by rewriting it, we were able to simplify. All right, let's look at this next one. Here we have 5x, all raised to the power of 3 over 2. So again, when our index is a 2, that's simply a square root. We don't write it, we just need to know that the index is a 2. And then our radicand is the 5x, and then all of that is cubed. So we do need to make sure we are cubing the 5 and the x. So if we simplify this a little bit, we get 5 times 5 times 5 times x times x times x. So we can actually simplify this. So remember, for square roots, we're looking for pairs. So here we have a pair of 5's and a pair of x's. So it simplifies to 5x times the square root of 5x. And there you go. All right, let's try one more together. So here we have 10x all raised to the power of negative 1/2. So for this one, let's first start with that negative. So remember, a negative exponent does not make our answer negative. It causes the term to become the reciprocal. So I'm going to rewrite it so we don't have the negative exponent anymore. The base still stays 10x. The exponent is still going to be 1/2, but once we flipped it, you can see it went from the numerator to the denominator. The negative has disappeared. And then from here, now we can rewrite it as a radical. So it's going to be 1 over the square root of 10x. Now here we do need to do one extra step in simplifying because our rule is we should never leave a square root in our denominator. So this next process is called rationalizing the denominator. We need to rationalize. And essentially we're trying to eliminate the square root again from our denominator. So when you have a square root, our goal is to create a pair so it disappears. So we just need to multiply by the square root of the same thing. So now we have a pair, but I can't just multiply on the denominator. I need to do the same thing on the numerator, like this. So my numerator becomes the square root of 10x. And in my denominator, since I'm multiplying these together, right, I have a pair of 10s, so that simplifies. It's like saying the square root of 100, which is 10. And I have a pair of x's, which is just x. So this is technically the simplified version. And again, it's just because we don't like to leave any type of radical in our denominator for the final answer. All right, so now we're going to practice going in the opposite direction. We're going to rewrite these radicals using rational exponents, and then we're going to simplify when possible. So in this first one, the base of our exponent is going to be that radicand, so 2. And remember, it goes inside, out. This is our numerator. This is the denominator. So it's 2 to the power of 8 over 3. So there's our rewrite, and we can't simplify this exponent, so we will leave it like that. All right, let's look at this next one. So you can see what our base is. Our base is 7x. We do need to make sure to include parentheses here, so to make sure that this whole thing gets the exponent we're about to create. If you don't have the parentheses, it would actually be wrong. So you can see that our numerator is going to be 5. And remember here, when it's a square root, our index is technically 2. We just don't write it. So it would be 5 over 2. So 7x all raised to the power of 5 over 2. And again, please make sure you have parentheses, or else you would only be raising x to the power of 5 over 2, which would be incorrect. All right, so let's look at this next one. So here again, we'll start with our base, which is y cubed in parentheses. This is going to be our numerator. This is our denominator. So to the power of 2 over 4. And now we can apply one of our rules of exponents. When we're raising a power to a power, we multiply the exponents. So this becomes y to the power of 6 over 4. And we multiply 3 to the numerator. And then this we can simplify. This becomes y to the power of 3 halves. And then last here, We have 1 over the cube root of 3x. So we'll say 1 over 3x in parentheses becomes our base. If we don't see an exponent here at all, we know that our numerator will be 1. And then since our index is 3, that becomes our denominator. So 1 over 3x, and remember you do need to have parentheses, to the power of 1/3. So now we've practiced going from rational exponents to radicals and from radicals to rational exponents. So for this try, you're going to be rewriting the rational exponents as radicals and vice versa. So you're going to rewrite and you're going to simplify when possible. So make sure you pause the video and give these a try on your own. And when you're ready to check, just hit play. All right, so go ahead and check. So anytime you have an exponent that's 1/2, it's essentially just the square root. So square root of 9 is 3. Here our base is 7 to the power of 6 over 3, which simplifies to 7 squared, which is 49. For part C, again, make sure you have parentheses around 6 and x. And then our exponent will be 5 over 2. Remember, square root has an index of 2. Now, part D is definitely a little bit trickier. I would not expect you to know how to do this. So hopefully you remembered that when you have the negative exponent, it flips it to the bottom if it used to be in the numerator. So notice we have 1 over 5 to the power of 2/5, so the negative is gone. And then we can rewrite this as 5 to the power of 2, and then that's a 5th root. So the 5th root of 5 squared. Now, if you got this far, that's great. Now, technically, we do need to rationalize because we don't like to leave the radicals in our denominator. So I'm trying to complete this group. So if I have the 5th root, I'm looking for a group of 5. And if I have 5 squared, that means I'm missing 3 powers of 5. If I had 3 more powers of 5, that would be a group of 5. So I'm actually going to multiply by the 5th root of 5 cubed. And again, we need to do that in the numerator and denominator. So when I multiply these, that creates my group of 5. So it just simplifies to 5. And then my numerator is 5th root of 5 cubed, which we could write as the 5th root of 125. Again, this is definitely more of a challenge problem, and rationalizing is not something that I'd expect you to be super comfortable with yet, but we will keep practicing. Okay? So that is all for today's video. Thank you so much for watching.